The paper discusses the potential detection of kinematic anisotropies in stochastic gravitational wave backgrounds, SGWB, using pulsar timing arrays, PTA. These anisotropies are induced by our relative motion with respect to the source rest frame and could provide valuable information about the physics underlying the gravitational waves. The author, Gianmassimo Tasinato, presents a comprehensive analysis of how these kinematic anisotropies can be detected and characterized in future PTA experiments. The introduction highlights the recent detection of a stochastic gravitational wave background signal by 4 PTA collaborations, which raises questions regarding its origin. Various sources, both astrophysical and cosmological, are compatible with current observations. To distinguish between these sources, properties such as parity violation, non-Gaussianities, and anisotropies can be explored. In the context of cosmological SGWB, kinematic anisotropies are expected due to our relative motion with respect to the cosmic rest frame. This motion has an amplitude of beta equals v, c equals 1.23 times 10⁻³ with respect to the velocity of light, pointing in the direction L. B equals 264 degrees, 48 degrees. The size of the dipolar kinematic anisotropy of a cosmological SGWB is estimated to be 1000 th smaller than the amplitude of the isotropic part of the GW spectrum, making it potentially larger than intrinsic cosmological anisotropies but smaller than astrophysical anisotropies in the PTA band. The paper aims to determine the pulsar response function to kinematic anisotropies, including effects related to parity violation, features in the frequency dependence of the isotropic part of the spectrum, and the presence of extra scalar and vector polarizations. It also explores how the sensitivity to different effects depends on the pulsar configuration with respect to the relative motion among frames. The author proposes strategies for detecting kinematic anisotropies, each designed to exploit future measurements for characterizing distinct features of the cosmological gravitational wave background. These strategies could significantly enhance our understanding of the underlying physics of gravitational waves and their sources. The paper discusses the potential for pulsar timing arrays, PTA, to detect kinematic anisotropies in the stochastic gravitational wave background, SGWB, which are crucial for probing various physical effects such as parity violation, frequency features in the GW spectrum, and the presence of extra scalar and vector polarizations. These anisotropies arise from Doppler boosting of the isotropic part of the SGWB due to relative motion between the observer's frame and the cosmic microwave background radiation, CMB, frame. The authors emphasize that current PTA measurements do not yet indicate SGWB anisotropies but anticipate future detections as data accuracy improves. They highlight the importance of understanding the geometrical aspects of the problem, particularly how the sensitivity to different GW effects depends on pulsar positions relative to the relative velocity vector among frames. This insight can be used to plan future PTA observations, especially with the forthcoming SCA facilities that will monitor a large number of pulsars. A pulsar timing array, PTA, experiment responds to an anisotropic stochastic gravitational wave background, SGWB, characterized by two key components: the GW intensity and GW circular polarization. To detect these effects, the analysis begins by examining the PTA experiment's response to an anisotropic SGWB. The gravitational wave, GW, is represented as fluctuations of the Minkowski metric, decomposed into Fourier modes, with the condition imposed for real GWs. The presence of a GW deforms the geodesics of light, resulting in a time delay on the period of a pulsar. This time delay is calculated using the detector tensor, which connects the light delay to the GW. The time residual is then computed from the time delay. The GW intensity and circular polarization are critical components of the anisotropic SGWB, which can be detected through their distinct signatures on the PTA experiment's response. The detection strategies for these effects involve characterizing the response of the PTA experiment to the anisotropic SGWB, taking into account the GW intensity and circular polarization. This foundational analysis sets the stage for applying the resulting formulas to the specific case of kinematic anisotropies in subsequent sections, enabling the exploration of novel detection strategies for these subtle yet important effects. The correlation between time residuals of a pair of pulsars, induced by the presence of a stochastic gravitational wave background, SGWB, is analyzed. The authors introduce the shorthand notation for the geometric factor and compute the two-point correlators of the two pulsar time delays. They utilize the assumption that the correlators of Fourier modes of GW fluctuations can be expressed as a function of the tensor SIL, F, N, which defines the properties of the SGWB. The tensor is decomposed into intensity and circular polarization components, I, F, N, and V, F, N, respectively. The correlation among time residuals is computed using the expression for the two-point correlators of the two pulsar time delays, involving integrating over frequency and direction. The expression is simplified by applying the properties of the correlators of Fourier modes of GW fluctuations, resulting in a more manageable form that includes terms related to both the intensity and circular polarization of the SGWB. The final result is then plugged into the expression for the two-point function of time residuals, providing a comprehensive framework for analyzing the response of a pulsar timing array (PTA) system to a SGWB with anisotropic intensity and circular polarization. The response of pulsar timing arrays to gravitational waves and their potential for detecting circular polarization in the stochastic gravitational wave background is discussed. The authors derive equations for the response functions of a pulsar paired to GW intensity and circular polarization, which depend on the relative position of the pulsars in the sky and the properties of the SGWB. For spin 2 GW modes, considering anisotropies induced by the motion of the reference frame with respect to the rest frame of the SGWB source, the response functions gamma I and gamma V are computed using angular integrals over all directions. The quantity in equation, 2.18, is an odd function of the vector directions, integrating to 0 unless the circular polarization function V, F, N, depends explicitly on the direction n, requiring an anisotropic signal to measure circular polarization. The same procedure can be applied to study alternative gravity models where gravitation is mediated by a mixture of spin 2, spin 0, or spin 1 fields, examined in a later section of the paper. The formulas used for circular polarization are new in this context, while similar formulas for anisotropic GW intensity have been used in previous studies. The response of a pulsar timing array, PTA, to kinematic anisotropies in the spin 2 case, such as those predicted by general relativity, is investigated. This analysis considers possible effects of parity violation. Kinematic anisotropies are guaranteed properties of a stochastic gravitational wave background, SGWB, with a cosmological origin, making them promising probes for understanding the source of gravitational waves and the physics of gravitation. The gravitational wave frequency scales as f equals d⁻1f under a boost characterized by velocity v, where d is a function of the boost velocity and the direction of the gravitational wave. The SGWB intensity and circular polarization develop kinematic anisotropies in a moving frame, described by equations 3.4 and 3.5. These equations show how the isotropic background quantities I, F, and V, F, transform under boosts, introducing parameters n and alpha that control the tilt of the isotropic background. The kinematic anisotropies depend on the pulsar location in the sky, the frequency dependence of the isotropic part of the SGWB, and the presence of parity-violating effects. The transformation of the isotropic background under boosts results in kinematic anisotropies that could be detectable with PTA experiments, potentially providing insights into the properties of the SGWB and the underlying physics of gravitation. The pulsar response functions to gravitational wave intensity and velocity are derived and analyzed up to order beta squared. The response function for gravitational wave intensity, gamma EOB, consists of three components: the Helling-Downs curve, gamma h dab, a first-order kinematic term, f(1) ab, and a second-order kinematic term, f(2) ab. The Helling-Downs curve is independent of the relative velocity beta, representing the classic result. The kinematic terms introduce anisotropies in the pulsar timing array signal, with the first-order term proportional to the slope of the stochastic gravitational wave background profile and the second-order term contributing to both dipolar and quadrupolar anisotropies. These kinematic terms are geometrically dependent on the relative positions of the pulsars and the Earth, vanishing when the pulsar directions are orthogonal to the relative velocity vector. A useful geometric combination, YAB, is introduced, simplifying the expressions for the response functions and aiding in understanding their geometrical properties. The figure illustrates the contributions to pulsar timing array, PTA, response functions for gravitational wave, GW, intensity and circular polarization, depending on the angle zeta among pulsar directions. In the left panel, we observe the dipole response to GW intensity and circular polarization, while the right panel depicts the quadrupole response to GW intensity and circular polarization. The Helling-Downs curve is also included for comparison. This analysis highlights the importance of anisotropies in the GW background for detecting circular polarization, which vanishes for an isotropic background. The quadrupole response is found to be suppressed by a factor beta 2. But can be enhanced by frequency-dependent spectral features. This research emphasizes the need for anisotropic backgrounds to measure effects due to parity violation, similar to what is required for planar interferometers like LISA. In essence, this study underscores the significance of considering directional variations in the gravitational wave background when using pulsar timing arrays to detect circular polarization. By examining both dipole and quadrupole responses, it becomes clear that isotropic backgrounds are insufficient for detecting circular polarization, and that anisotropic backgrounds play a crucial role in enhancing the quadrupole response. These findings have implications for future experiments aiming to measure parity violation, such as those utilizing LISA, and demonstrate the importance of accounting for directional variations in GW backgrounds. In the realm of pulsar timing arrays, PTAs, kinematic anisotropies have emerged as a crucial area of investigation. These anisotropies are intricately linked to the frequency slope of the circular polarization function, which differs significantly from gravitational wave, GW, intensity detection. The geometrical configuration of the system plays a pivotal role in this context, making it challenging to represent graphically. The authors of the study emphasize the importance of understanding the stochastic gravitational wave background, SGWB, frequency dependence. This can be exemplified through broken power law profiles and complex profiles motivated by primordial black hole physics. These scenarios have profound implications for kinematic anisotropies, particularly in terms of the parameters controlling the intensity profile and their subsequent impact on tilt parameters. To elucidate further, kinematic anisotropies in PTAs are influenced by the distribution of pulsars within the array. This distribution can lead to variations in the observed gravitational wave signal, affecting the overall sensitivity of the array. By examining the frequency slope of the circular polarization function, researchers can gain insight into these anisotropies and their potential impact on GW detection. Moreover, the SGWB frequency dependence is a critical aspect of this research. Different models, such as broken power laws or those inspired by primordial black holes, can significantly alter the expected signal. For instance, a broken power law profile may indicate a change in the underlying physical processes driving the GW emission at different frequencies. Similarly, models incorporating primordial black holes suggest the possibility of distinct signatures in the GW spectrum. The consequences of these scenarios on kinematic anisotropies are multifaceted. For example, variations in the intensity profile can influence the tilt parameters, which in turn affect the overall anisotropy observed in the PTA. This interplay between intensity profile and tilt parameters underscores the complexity of the system and the need for a nuanced understanding of the underlying physics. In conclusion, the study highlights the importance of considering kinematic anisotropies in PTAs, particularly in relation to the frequency slope of the circular polarization function and SGWB frequency dependence. By delving into these complexities, Researchers can refine their understanding of GW emission and improve the sensitivity of PTAs for detecting these elusive signals. The intensity spectrum profiles and combinations of slope parameters characterizing kinematic anisotropies are central to understanding the formation of primordial black holes. A broken power law profile is significant, as it suggests a complex interplay between different physical processes. This profile is further motivated by the physics of primordial black holes, which are hypothetical objects that may have formed in the early universe before the first stars. The second-order gravitational wave, GW, from primordial black hole formation is another key aspect of this research. The expected frequency profile of these GWs is crucial for understanding their potential impact on the universe. The GW energy density, denoted as omega GW, F, plays a pivotal role in this context. It is related to the intensity parameter, I, F, through the relation F3I, F, proportional omega GW, F. This means that the intensity parameter can be used to estimate the GW energy density, providing valuable insights into the universe's early stages. The behavior of the intensity parameter is critical for understanding primordial black hole formation. Its variations can reveal information about the physical processes involved in the formation of these hypothetical objects. By examining the intensity parameter's behavior, researchers can gain a deeper understanding of the universe's early stages and the potential role of primordial black holes in shaping cosmic evolution. This research has significant implications for our understanding of the universe's origins and the nature of black holes. In theories of gravity alternative to general relativity, scalar and vector metric components participate in gravitational interactions, contributing to the gravitational wave signal through extra polarizations. These theories' PTA responses to scalar and vector polarizations have been derived for isotropic backgrounds, inducing correlations among pulsar signals distinct from the Helling-Downs curve. Recent detections can be used to set upper bounds on scalar and vector contributions to isotropic backgrounds. This paper derives analytical formulas for the PTA response functions to kinematic anisotropies associated with scalar and vector polarizations. The procedure follows that of sections 2 and 3 for the tensor case, utilizing scalar and vector GW polarization tensors. The scalar and vector polarization tensors are used to perform angular integrals corresponding to equations 2.15 and 2.16. Scalar contributions to the GW signal are characterized by scalar intensity, with no circular polarization. The total isotropic part of the intensity is composed of tensor and scalar parts, with slope parameters defined in equations 4.1 and 4.2. The PTA response function to the scalar part of the intensity is given by equation 4.3, which includes dipolar and quadrupolar kinematic anisotropy contributions. Notably, the PTA response to scalar kinematic anisotropies is independent of the angle among pulsars, but depends on the angles among pulsar directions and the frame velocity vector. This response is proportional to the slope of the scalar contribution to the total intensity, making it a unique probe of this feature. Vector tensor non-minimally coupled theories of gravity have also been introduced, with correlators among vector Fourier modes decomposable into intensity and circular polarization. These theories offer new avenues for testing gravity beyond general relativity using PTAs. The paper discusses the kinematic anisotropies in pulsar timing arrays, PTA, as a probe for specific properties of the stochastic gravitational wave background, SGWB. It highlights the geometrical configuration of the pulsar network's role in response functions, which depend on the intensity and circular polarization of the SGWB. The response to GW intensity is maximized when pulsars' positional vectors align with the Doppler velocity vector, while the response to GW circular polarization is enhanced for pulsars on a plane perpendicular to the Doppler velocity vector. The paper provides equations for computing the PTA response to dipolar anisotropies of the vector intensity and vector circular polarization, showing a strong dependence on the angular separation among pulsars. Figure 3 illustrates the PTA response to an isotropic scalar GW component, dipole response to scalar GW intensity, and quadrupole response to scalar GW intensity. as well as the PTA response to an isotropic vector GW component, dipole response to vector GW intensity, and dipole response to vector GW circular polarization. These responses are functions of the angle zeta among pulsar directions, demonstrating how kinematic anisotropies can be used to probe the properties of the SGWB. In this section, the authors discuss the potential applications of kinematic anisotropies in the detection of various physical effects within a stochastic gravitational wave background, SGWB. They emphasize that these anisotropies can be exploited to extract information about the gravitational wave signal, particularly concerning parity violation, the frequency slope of correlation functions, and the presence of extra polarizations. The authors first focus on the detection of circular polarization, which is a key indicator of parity violation in the SGWB. By carefully selecting pulsars for monitoring, statistical errors can be minimized, and the signal-to-noise ratio, SNR, for detecting circular polarization can be maximized. This is achieved when pulsars are positioned such that their position vectors lie on a plane orthogonal to the velocity vector, reducing possible contaminations from kinematic effects due to GW intensity. The authors then present a formula for the optimal SNR for detecting the presence of circular polarization in PTA time delay correlators, which involves the product of several terms including the observation time, the amplitude of the circular polarization, the response function to circular polarization, and the noise spectral densities of the pulsars. This formula provides a quantitative measure of how effectively kinematic anisotropies can be used to probe parity violation in the SGWB. Furthermore, the authors note that kinematic anisotropies can also be used to probe the frequency slope of correlation functions, which is difficult or impossible to extract from the isotropic part of the background alone. This property applies not only to standard spin-2 polarizations but also to backgrounds containing spin-0 and spin-1 contributions. Hence, a detection of kinematic anisotropies can provide a complementary probe of the slope of GW polarization components. Finally, the authors suggest that kinematic anisotropies can serve as a probe for the presence of extra polarizations, such as those predicted by certain theories beyond general relativity. By analyzing the deviations in signal correlations among pulsars from the standard Helling-Downs angular distribution, researchers can gain insights into the polarization properties of the SGWB and test the validity of general relativity. The authors investigate a random collection of pulsar pairs with positional vectors orthogonal to the relative velocity, examining how geometrical factors dependent on the relative velocity affect the response functions for circular polarization as a function of the angle zeta between pulsars. Figure 4 illustrates the left combination of the random realization, which decreases as zeta approaches 0 and pi. The right panel shows the Helling-Downs distribution and the response function for the random realization, including the circular polarization kinematic dipole, with beta n equals 1/10. The points are scattered with respect to the black line for intermediate values of zeta. The circular polarization response function gamma vab, given in equation 5.1, is derived, which depends on the slope of the quantity v, f, and might be enhanced if v, f, is a steep function of frequency. This study of kinematic anisotropies could represent the only way to probe the frequency dependence of quantities associated with circular polarization. To detect parity-violating effects, a factor of 1, beta asymptotically equal 1000 more in sensitivity with respect to current experiments would be required in the most conservative cases. The authors also discuss kinematic anisotropies and stochastic gravitational wave background, SGWB, intensity. The corresponding response function gamma EOB of a pulsar pair, A, B, to intensity Doppler effects is given by equation 3.9, rewritten up to the dipole contributions in equation 5.2. This function depends on zeta through the Helling-Downs curve gamma h dab and also on the angle each pulsar vector forms with the relative frame velocity v. Only pulsars whose vector components lie along v are sensitive to kinematic anisotropies relative to the GW intensity. The authors consider a random collection of pulsar pairs whose positional vectors lie on the same plane as the relative velocity vector. They aim to represent how geometrical factors depending on the velocity vector affect the response functions as a function of the angle zeta among pulsars. The left panel of Figure 5 shows the combination of Vxa plus Vxb for a random realization of pulsars, as a function of zeta. The size of this quantity decreases as zeta approaches pi. The right panel of Figure 5 displays the resulting response function gamma eob as a function of zeta, which is scattered for small angular separations zeta with respect to the Helling-Downs curve. This scattering is maximal for pulsar pairs lying in the same plane as the velocity vector and with positional vectors forming a small relative angle among themselves. This represents an interesting difference with respect to the GW circular polarization response. The kinematic effects are small, but by combining signals, null tests for Doppler effects associated with the intensity of the stochastic gravitational wave background, SGWB, can be formed. To find such combinations, the authors exploit the results of Section 3, assuming GW are characterized by spin-2 polarization only, with no effects of parity violation. They consider two pairs of pulsars. One pair, AB, lies on a plane parallel to the velocity vector, feeling the effects of kinematic anisotropies, and the response function up to the dipole is given by equation 5.2. The other pair, CD, lies on a plane orthogonal to the velocity vector, being blind to Doppler effects, and the pulsar response function is determined only by the Helling-Downs curve of equation 3.10. The section discusses the contributions of kinematic quadrupoles to the angular dependence of the PTA response functions. A plot, Figure 6, complements previous figures by illustrating the quadrupole's impact. The left panel shows a random realization of the quadrupole contribution to the intensity response function, and the right panel presents a similar realization for the circular polarization response function. The discussion emphasizes the significance of kinematic anisotropies in enhancing sensitivity to features in the frequency dependence of GW correlators, particularly for signals with intensity slope features. It also touches on the role of scalar contributions to the GW signal, highlighting their potential to be disentangled through kinematic anisotropies in scenarios with pronounced frequency dependence. The intensity slope parameters, defined in equations 4.1 and 4.2, enable the decomposition of the pulsar timing array, PTA, intensity response function to Doppler dipolar anisotropies in scalar tensor theories into isotropic and dipolar components, as shown in equation 5.5. The isotropic component, gamma street, isoab, describes the pulsar response to the isotropic part of the scalar tensor intensity, while the dipolar component, gamma street, dipab, represents the pulsar response to the dipolar kinematic anisotropy. Even with a small scalar contribution to the intensity, a pronounced slope dependence can make the dipolar component sensitive to scalar polarizations. By combining signals from different pulsar pairs, following the method described around equation 5.3, the effects of scalar dipolar anisotropies in the response functions can be isolated, allowing for the detection of scalar polarizations even if they contribute only a small part to the gravitational wave signal amplitude. The recent detection of a stochastic gravitational wave background by pulsar timing array collaborations has opened a new window for gravitational wave cosmology. The presence of kinematic anisotropies in the stochastic background can provide valuable physical information, including the ability to detect parity violation in gravitational interactions, scalar or vector polarizations, and independent probes of the frequency profile of the stochastic background. These findings can inform the planning of future measurements or the elaboration of existing data to detect or constrain these effects. The application of these results to astrometric measurements of gravitational waves based on Gaia data is also of interest. Current measurements set upper bounds on the amplitude of multipoles of the stochastic gravitational wave background, but future measurements, such as those by the SCA collaboration, are expected to provide more stringent constraints. The theoretical study of the stochastic gravitational wave background, SGWB, focuses on its anisotropic properties, emphasizing the importance of considering frequency-dependent SGWB models, particularly those motivated by early universe models producing primordial black holes. It highlights that such models cannot be explained by the factorizable ansatz commonly used in the literature. Instead, it proposes a SGWB with enhanced frequency dependence, which can amplify kinematic anisotropies to values significantly larger than expected. The study assumes the direction and amplitude of the velocity vector between the cosmological source and the solar system barycenter coincide with those measured by the cosmic microwave background dipole. It suggests that gravitational waves could serve as an independent probe of the cosmic dipole, allowing for tests of alternative scenarios such as large-scale super-horizon isocurvature fluctuations or intrinsic anisotropies. The authors introduce the circular polarization indexes, denoted as lambda equals plus or minus 1, corresponding to right and left-handed circular polarization. In the circular basis, the polarization tensors can be expressed as a product of polarization vectors, E lambda ab, n, equals E lambda a, n, E lambda b, n. These vectors are further decomposed into real unit vectors pa and ka, which are orthogonal to each other and to the gravitational wave direction n. The Levi-Civita tensor EABC is used to express ka in terms of pa and nb. Several identities involving the symmetric and antisymmetric combinations of pa and cube are derived. Specifically, PAPB plus K cube equals delta ab nanb, and P cube pbk equals EABCNC. Using these identities, the authors establish the relation between the circular polarization basis and the original, plus, times, polarization basis. The product of polarization tensors E lambda ab, n, and E lambda, cd, n, is expressed in terms of the Kronecker delta and the Levi-Civita tensor, leading to the identities in equations, A.14. These identities relate the circular polarization tensors to the original polarization basis, facilitating the analysis and providing a compact and convenient form for the polarization tensors. The use of the circular polarization basis and the Levi-Civita tensor is crucial for the derivation of these identities, which are essential for the overall framework of the paper. The polarization tensors for spin 0 and spin 1 modes are discussed in detail in this section of the research paper. For spin 0 polarization tensors, equation A.16 is used to derive equation 4.3 from the main text. In the case of spin 1 polarization tensors, a circular R, L basis and vector polarization tensors are introduced, as given by equation A.17. Several identities for these tensors are then derived, including equations A.18, A.19, and A.20, which are essential for obtaining equations A.21 and A.22. These equations play a critical role in understanding the PTA response to GW intensity and circular polarization, as well as for computing the optimal signal-to-noise ratio discussed in the subsequent section. The paper also delves into the computation of the signal-to-noise ratio using a match filtering technique, as described in the referenced paper and textbook. This section focuses on the spin 2 case, providing a comprehensive analysis of the polarization tensors and their implications for gravitational wave detection. The detailed equations and identities presented in this section are crucial for understanding the polarization properties of different spin modes and their impact on the sensitivity of pulsar timing arrays, PTAs, in detecting gravitational waves. The authors derive the stationary two-point correlator for time delays of pulsar measurements summed over a pulsar timing array set of pulsar pairs, assuming noise dominance over the signal. This correlator is expressed in both time and frequency domains, utilizing the finite time delta function and the Fourier transform of the noise correlation function COB. In the frequency domain, the correlator is decomposed into real and imaginary parts, QIAB and QVAB, which are functions of frequency. The signal-to-noise ratio, or SNR, is defined as the ratio of the averaged value of the correlator when the gravitational wave signal is present to the root mean square of the correlator when the signal is absent. The signal S is expressed as the averaged value of the correlator when the gravitational wave signal is present, using the two-point correlator in Fourier space. This two-point correlator is derived using formulas developed in section 2, and is expressed in terms of the noise correlation function and the gravitational wave signal. Noise n is computed using the textbook treatment, and is expressed in terms of the noise correlator and the gravitational wave signal. The SNR is then derived, and is expressed as a function of the gravitational wave signal, the noise correlator, and the filter functions QIAB and QVAB. Optimal filter functions QIAB and QVAB are determined by maximizing the SNR, which is a function of the gravitational wave signal and the noise correlator. This approach provides a new method for optimizing filter functions to extract the gravitational wave signal from the noise, a critical quantity in detecting gravitational wave signals in pulsar timing arrays. Optimizing the filter function to maximize the signal-to-noise ratio, SNR, is crucial in gravitational wave detection. This involves constructing a tensor with a specific structure, comprising positive definite products of A1 and A2. The SNR is formulated using a mathematical tool, allowing for the expression of the SNR of a given equation. Different filter options are explored to achieve optimal SNR performance. One approach is to maximize the total signal, which yields an SNR equation dependent on the gravitational wave intensity and circular polarization, as well as geometric quantities. Another option is to extract circular polarization components, resulting in a distinct SNR equation that incorporates these parameters. A third approach involves enhancing sensitivity to gravitational wave intensity, leading to a unique SNR equation that takes into account the relevant factors. Each filter option yields a specific SNR equation, highlighting the intricate relationships between gravitational wave intensity, circular polarization, and geometric quantities. Understanding these concepts is essential for optimizing the sensitivity and specificity of gravitational wave detectors. By carefully selecting the filter function, researchers can maximize the SNR, thereby enhancing the detection capabilities of these sophisticated instruments. The research focuses on gravitational waves, particularly in the context of pulsar timing arrays. It discusses various studies on the isotropic gravitational wave background, stochastic gravitational wave backgrounds, and the search for gravitational wave signals. The papers also explore parity-violating interactions, non-Gaussianities, and the potential for detecting primordial black holes. The methodologies used, significant findings, and implications of these discoveries on our understanding of the universe are highlighted. The analysis of anisotropies in the gravitational wave background is crucial for understanding the universe's early stages. Key studies by Kogut et al., WMAP collaboration, and Planck collaboration have contributed significantly to our understanding of the cosmic microwave background and its relation to the gravitational wave background. Pulsar timing arrays, discussed in Cornish and Sasana, Taylor et al., and Chung et al., are essential for detecting and characterizing the stochastic gravitational wave background. It's important to consider anisotropies and non-Gaussianity in the gravitational wave background when interpreting data from these arrays. The paper also explores the impact of Doppler boosting, as discussed in Cusson and Tasinato, which can significantly alter the observed spectrum, particularly at low frequencies. Additionally, projection effects, studied by Bertacca et al., can introduce additional anisotropies that must be accounted for. The dipole anisotropy of the astrophysical gravitational wave background is also addressed, highlighting the complexity and importance of these factors in understanding the universe's early stages. Detection and mapping of anisotropies in the stochastic gravitational wave background is a crucial step towards understanding the universe's underlying physics. Current models, however, are limited to isotropic descriptions, neglecting potential directional variations. To address this limitation, a novel method is proposed, leveraging the Fisher information matrix and Bayesian techniques to detect and map anisotropies. The approach relies on a network of ground-based laser interferometers, which can probe the stochastic background and map the sky for anisotropies. This mapping can provide valuable insights into the sources contributing to the background. The Laser Interferometer Space Antenna, LISA, is expected to offer high angular resolution in its observations, enabling more precise mapping of the gravitational wave sky. The proposed method utilizes the Fisher information matrix to quantify the uncertainty in the anisotropy parameters. Bayesian techniques are then employed to reconstruct the anisotropy map, allowing for a probabilistic interpretation of the results. The authors demonstrate the efficacy of this approach through simulations, showcasing its ability to detect and map anisotropies in the stochastic gravitational wave background. The paper highlights the significance of anisotropy detection and mapping, as it can reveal valuable information about the sources driving the stochastic background. The proposed method offers a promising approach for achieving this goal, paving the way for a deeper understanding of the universe's gravitational wave landscape. In the realm of gravitational wave astronomy, the detection and analysis of stochastic gravitational wave backgrounds have garnered significant attention. This area of research holds promise for unraveling the fundamental physics of the universe. A crucial aspect of this pursuit is measuring the circular polarization of stochastic gravitational wave backgrounds, which can provide invaluable insights into the universe's underlying mechanisms. To achieve this, researchers employ various methods, including correlation signals from ground-based interferometers, such as the Laser Interferometer Gravitational Wave Observatory, LIGO, and pulsar timing arrays. The NANO-GRAV collaboration has made substantial contributions to the search for anisotropy in the gravitational wave background. Multiple studies have explored the potential for detecting circular polarization using these approaches, as well as the prospects for future experiments like the Square Kilometre Array, SKA, and the Einstein telescope. Theoretical aspects of gravitational wave backgrounds are also crucial, with the chirality of the background having significant implications for our understanding of the universe. The reconstruction of the spectral shape of a stochastic gravitational wave background with LISA, a space-based interferometer, has been investigated. This research area is characterized by its complexity and depth, with numerous studies developing and applying techniques for detecting non-Einsteinian polarizations of gravitational waves. A unified treatment for the analysis of stochastic gravitational wave backgrounds is essential. Various detection methods, including the use of tensorial and non-tensorial polarization modes, have been discussed in the literature. The importance of circular polarization measurements cannot be overstated, and future experiments are poised to significantly advance our understanding of the universe. Gravitational wave backgrounds hold significant implications for our understanding of the universe. Pulsar timing arrays have been explored as a means to test general relativity and detect stochastic gravitational wave backgrounds, as demonstrated by several previous studies. The Hellings and Downs correlation curve is a crucial concept in this context, highlighting the isotropic nature of gravitational waves. However, considering anisotropies in the gravitational wave background is essential, as they could provide valuable insights into the sources of these waves. Different theories, such as those involving primordial black holes, can be tested using pulsar timing arrays. Moreover, disentangling multiple stochastic gravitational wave background sources in PTA datasets is necessary to accurately identify the origins of these waves. The possibility of enhancing gravitational wave anisotropies with peaked scalar sources is also explored, which could reveal more about the universe's early stages. The cosmological gravitational wave background from primordial density perturbations is a critical area of focus, as these perturbations significantly shape our understanding of the universe's evolution. The authors emphasize the importance of considering these perturbations in the context of gravitational wave backgrounds. By examining the stochastic gravitational wave background, researchers can gain valuable insights into the universe's evolution, from the early stages to the present day. The implications of primordial black holes and scalar-induced gravitational waves on the cosmic microwave background radiation, as well as their potential detection methods, are explored in this section of the research paper. Several studies have investigated these topics, including the work by Bowman et al. 107, which discusses the gravitational wave spectrum induced by primordial scalar perturbations. Saito and Yokoyama, 108, 109, have also examined the gravitational wave background as a probe of the primordial black hole abundance. The paper also delves into the astrometric effects of a stochastic gravitational wave background, as explored by Book and Flanagan, 119, and the constraints on the polarization content of gravitational waves with astrometry, discussed by O'Byrne and Cornish, 122. Furthermore, it highlights the potential for future surveys to detect primordial black holes through their gravitational lensing effects, an idea proposed by Erashenko, 110. The authors also emphasize the importance of considering the possible impact of primordial black holes on the large-scale structure of the universe, as suggested by Carr and Silk, 111. In conclusion, This section of the research paper provides a comprehensive overview of the implications of primordial black holes and scalar-induced gravitational waves on the cosmic microwave background radiation, along with their potential detection methods. It highlights the significance of ongoing and future surveys in shedding light on these enigmatic phenomena, which could revolutionize our understanding of the universe's early stages and the nature of gravity itself. The observed tilt in the universe's orientation poses significant challenges to the standard cosmological model, suggesting the possibility of an entropy gradient or a boost in the universe's velocity. This anomaly could have profound implications for our understanding of the universe's evolution, emphasizing the need for a more nuanced comprehension of the cosmos. Multimessenger cosmology, which involves correlating diverse cosmic signals, such as the cosmic microwave background and stochastic gravitational wave background measurements, can provide valuable insights into the universe's structure and evolution. Furthermore, cross-correlating astrophysical and cosmological gravitational wave backgrounds with the cosmic microwave background can help researchers understand the interplay between these signals, gaining a deeper understanding of the universe. The upcoming generation of cosmic surveys and gravitational wave detectors will enable scientists to probe deeper into the universe, potentially uncovering new insights that could challenge or refine our current understanding of the cosmos. Therefore, continued research in these areas is crucial, as it can help address the limitations of the standard cosmological model and provide a more accurate understanding of the universe's evolution. The significance of multimessenger cosmology and cross-correlation techniques lies in their ability to uncover novel insights into the universe's structure and evolution. By leveraging these approaches, researchers can gain a deeper understanding of the interplay between different cosmic signals, ultimately refining our comprehension of the cosmos.